First time I remember hearing it beep like that when I punched it, pressed it. All right, we are now recording. I've already made all the announcements in the previous class, and since all three of you are in the same class, I won't repeat those again. For some reason, it started on the wrong slide. Now, my memory here, any questions on anything we've done so far in differential equations?
When you're given, say, an Euler procedural method,
Right.
and normally we started y of 0 is equal to some number.
Right.
But I'm not asking you to work the problem, but
Right.
He does that in the text too. But he doesn't explain it. But he starts it y is equal to 1.
Yeah.
And
Okay, is this referencing the most recent test?
yeah, it's referencing that.
Yeah.
I went back and looked at the last assignment.
Yeah.
And he had that kind of problem in there, but he
Right.
never showed an example of how he got there on the.
Right. I think I understand what you're asking. Let's see.
And he did something we normally do by parts, and he doesn't explain what the reality is.
Yeah. Well, now, actually, the example 1 that we did on page 78, you're starting from x equal 2, y equal 4. Page 78. See, it says y of 2 is equal to 4. That's your starting point, and you're trying to get up to y of 2.5. And it said first use a h of 0.1 and then a 0.05. Then the next example 2 at the bottom of the page, starts at 1, 1. X equal 1, y is equal to 1. And you're estimating what it will be at 1.5, again using first 0.1 and then 0.05. And that's what they showed here. Okay, the one on your test is starting at x equal 1, y is equal to 9. So you only go 2 more steps to get to 1.2 when you have the h of 0.1. So this is a lot shorter than the others. So what's in the parentheses following the y is the x value, and what's outside the parentheses after the equal sign is your y value. So, huh?
Yeah, I got that.
Oh, okay. I misunderstood your question then.
No, you answered the question. I just didn't pick up on that.
Yeah. So you just do.
I think it's just an X to me off rather than. Yeah, both threw me off. Okay, I'll have to read it again. I'll go back to page 78.
Mm-hmm.
Yeah, that's what threw me off. Yeah. Well, there are 2 unknowns in there. The one you're going to figure out, but it's not figured out. What's on the radical is always the n minus 1 term.
Yeah. Yeah, your first one, what goes in the radical is your first y, which is 9. So that would be Yeah, that's your 1. And this, on that first step, the x is 1, the y is 9. And then your next step, and that gives you what y, okay, this is your y prime, which I think they call the f or whatever, you know, and then you multiply that by your h, which is your 0.1, and that's how much you increase the y. No, I'm sorry. This gives you your first estimate. Your y0 plus your h times your, what they're calling your f of xy. That's actually your what is the first? Yeah, that's your y prime, is what they're calling your f of xy, which seems a little bizarre because you think of y prime being f prime, but it's not. That is your y prime here. So your first estimate, y1, would be, goodness, my nose is itching, your y0, which is 9, plus h times this derivative, with x being 1 and y being 9. So that gives you your y1, and then, okay, and that y1 is 1.1 because you've just increased it by, your x value is now 1.1. So your y of 1.1, you plug that in to do your next y2, and it would be your previous y value got from here, plus then the h times this thing again, but with the new x's and y's in there. It's, everything's changing a little bit every half step, you know. That probably didn't make a lot of sense. What's that? Yeah. Is that it, or any others? Okay. My nose is itching like crazy. The old days, my grandmother used to say, that must mean you're going to have company. I don't know if you've ever heard that one. But, okay. Oh. What was that? Yeah. Oh, I see. I've never had that. That's too bad. Okay.
Every time it started itching, I said, I never done anything.
Right, exactly. All right. So we're in chapter 4, which is higher order differential equations. 4.1 is one long, drawn-out section here, covering a lot of different little things before we ever get to solving any higher order differential equations. These are all setting us up for what we're going to come next. And what we've done so far in 4.1, at the very beginning of 4.1, we just dealt with the preliminary theory and some terms. 4.1.1 is initial value and boundary value problems, which have initial value problems, some aspects of what we're going to do. Yeah, we're going to do some of those. Then we did 4.1.2, which is your homogeneous or homogeneous equation. That's when that differential equation of higher order is equal to 0. Okay? And then we did a lot of different things with that, superposition, independence, dependence, Wronskian, all those kind of things. General solutions of a homogeneous or homogeneous equation. And then we finally get to 4.1.3, which is where we're beginning today. What if the right-hand side is not equal to 0? Okay? Now, they start with, let me get my pen set up. Any function y sub p. Now, the p stands for particular. You're going to get to that in a second. But these are free of arbitrary parameters. My writing stinks. Okay? That satisfies 7, that's your original differential equation, is said to be a particular solution. That's what the P stands for. It says, for instance, a straightforward task to show that the constant function y sub p is equal to 3 is a particular solution for this. It's a higher order, non-homogeneous equation, y double prime plus 9y is equal to 27. Now later we're going to learn how to solve that. I wish they'd go on and show us how to solve it, so then we wouldn't be so much hypothetical here. But whatever solutions you get there, it's going to be a two-parameter system. A C1 with some things and C2 with something else. Okay? But what they're saying here, if you can come up with any other solution other than those two, and these solutions you never put a parameter with. Okay? And it says, what if y is equal to 3? Okay? Well, y prime is equal to y is 0, and y double prime would be 0. So then you have 0 plus 9 times 3. Sure enough, that's 27. So that's also a solution. Y is equal to 3 will be a solution, in addition for all those that had the parameters with them. Okay? So let's say your others came up with y is equal to C1 y1 of x plus C2 y2 of x. Well, now that you have another one, you just add plus 3. That's going to be another one because that is also a solution. But it doesn't have a parameter with it. The non-homogeneous ones will always produce the parameters. The homogeneous part, or homogeneous part will produce a parameter. The right-hand side will not. Okay? Now, again, they haven't told you enough for that to be making good sense yet. But in general, what we mean by that, and I think I'll start over because I've used too much of the page here. To phrase another word, if y1, y2, y3, ... up to y sub n, or is that what they're using now? No, k, okay? Y sub k are all solutions of that homogeneous part. I'm not going to write down what it is. You know, that homogeneous part. A sub n, A sub, whatever that would be. I probably, X raised, the ith derivative, and you step on through it. If all those are solutions of the homogeneous part, that's the equation 6, okay, on some interval I, and y sub p is a particular solution. That if you put something on the right-hand side, You can also come up with a y sub p that'll make that true using that same set of equations over there. So the y1 through yn are all coming from your your homogeneous part, and if you have some particular solution that comes from the right-hand side, okay, that's a yp, okay. Now, what we're going to get to later, you can see you can have more than one yp's, but let's just leave it at this. Is also a solution. Then the linear combination, this is your superposition principle, that your general solution, y, is going to be some c1 times the y1 plus c2 times the y2 plus c3 times the y3 plus dot 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 plus c sub k times y sub k plus yp. So you take all those that were your general solution of the homogeneous part and then add to it any particular solutions you have out there. Those particular solutions do not have arbitrary coefficients. These do. You have to put them in there. And they can be any numbers in the world. The yp's, they don't have any arbitrary coefficients. They just have the function. Okay? And again, this is sort of presented to you in a vacuum because they haven't quite told you what all these things are yet. Okay. That will then be a solution of the non-homogeneous part. That's the part that has the equal g of x on the other side. Okay. They're always referring back to equations 6 and 7. 6 is the homogeneous part. 7 is if it has a g of x.
In this case, the yp would force to be a non-homogeneous equation.
Yeah, that would be the right-hand side of the non-homogeneous. Exactly. Okay. If you think about it, this makes sense, they say. Yeah, sure, okay. And then they get into the operators and show you how much sense this makes. And just introducing those operators almost make it doesn't make any sense. But anyway, we won't get into that. But anyway, so here's the theorem which supposedly summarizes, wraps all this up, ties it in a pretty bow. Okay? Let y sub p be any particular solution. What is, I don't know, particular okay, of the non-homogeneous linear nth order differential equation, DE, yuck, I can't write, okay, and that was the one they're calling number 7, one that has a g of x on the right-hand side, non-homogeneous, on an interval I, and let, so that's your y sub p for the non-homogeneous, the right-hand side, and let these, your y sub 1, y sub 2, y sub 3, dot, 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 up to this time they're using y sub n. They sort of change them every now and then, I don't know why. Be a fundamental set of solutions, remember, be a fundamental set of solutions. Okay, remember the fundamental means they're all linearly independent of each other, and they're, if you have an nth order differential equation, you have to have n of these fundamental equations. They all have to be linearly independent of each other. That makes them a fundamental set of solutions. Okay? Of the associated homogeneous differential equation. So in other words, the non-homogeneous is all this differential equation part. All your nth derivative, then minus first derivative, minus second, all those derivatives down to h of 0, y. The homogeneous part would be if that's equal to 0. So that would be those, the y1s, y2s up to yn. Those would solve that. But on the non-homogeneous, you'd have something else, g of x on the other side. Anything that would satisfy that with these same things, those would be your particular solutions. Okay? So the associated homogeneous part is when you set that g equal to 0 and you just deal with the homogeneous. That gives you your y's up there, up to yn. Okay? On I. Okay? Everything's on the same interval I. Then, the general solution would be of the equation on that interval okay, is y is equal to C1 y1 of x plus C2 y2 of x plus C3 y of, put my parentheses in the wrong place, C3 of y3 of x plus dot 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 plus C sub n y sub n of x plus any of these y sub p's with no arbitrary coefficients. None. Okay? You just put the y sub p's at the end. These are also functions of x. Those are anything that would solve that same homogeneous part, the same homogeneous part to make it equal the part that's non-homogeneous, the g of x at the other end. Okay. And these CI's where I 1 less than or equal to I less than or equal to n are your arbitrary coefficients. Okay. Constants. Okay. Now, they prove it using those L operators, which are perfectly fine. Go to town with it if you'd like. Now, what we were calling the associated homogeneous part, the set of solutions of the, let me phrase it this way. This set of solutions here, everything that solved the homogeneous part, the C's, the Y's, all those things that solved the homogeneous part, that's called the complementary function. Okay? That linear complement, y sub c, we're going to call it, is everything that's inside the parentheses. Okay? All those arbitrary coefficients with their associated linearly independent y functions that make your fundamental set of solutions, that is called the y sub c. And then your general solution, y, is your y sub c plus any of your y sub p's, which are your particular solutions. And they're all functions of x. So the complementary part is the part that solved your homogeneous portion, okay? So your complementary function plus any functions plus any particular solution, any, there may be more than one, that will be your general solution. Now, let's see if an example clarifies it or muddies it, okay? We'll see. Do you need this any longer? Okay. By substitution of the function y sub p is equal to minus 11/12, they pick a very realistic one, minus 1/2 x, is readily shown to be a particular solution for this non-homogeneous differential equation. Y triple prime minus 6y double prime plus 11 y prime minus 6y is equal to 3x. Okay?
This is some work.
What's that?
I said, this is some work.
Yeah. It says by substitution, this function is readily shown to be a particular solution for that. What that means is we got to take those derivatives. So what's your yp prime?
Y prime is minus 1/2.
Minus 1/2.
Minus 1/2.
That's it. And your y prime, y particular double prime, 0. Y particular triple prime, 0. Okay? So this shouldn't be too hard to do. Readily shown. Okay? So this would be a 0 minus 6 times 0 plus 11 times a minus 1/2 minus 6 times 11. That was ugly. I started to make a pie out of it. I don't know what's going on here. Y particular would be minus 11/12 minus 1/2 x. And that is supposed to equal 3x. Let's see if it does. You distribute the 11 through that, it would be minus 11 halves, right? Then distribute the minus 6 through this part, you get plus 11 halves plus 3x. Is that equal to 3x? Sure it is. So, strange particular solution, but it is one that makes that true. Okay?
In this case, this is only one solution, right?
Yeah. They haven't told us the rest of them yet. Okay? It said to write the general solution for this, then we'd have to go back and figure out what the solution for y triple prime minus 6y double prime plus 11y prime minus 6y equals 0. That's going to be the complementary part, the things that here. That's going to be a 3-parameter system with 3 independent solutions, 3 arbitrary coefficients, and any linear combination of those. Okay? Now, it says in example 9, that was the last one we did right before, we saw that y1 equal e to the x, y2 equal e to the 2x, and y3 equal e to the 3x was a solution of that. They are linearly independent. We did the Wronskian of them, and it came out non-zero. So then we have, here is your general solution. Y is equal to C1 e to the x, I think it was, wasn't it? Yeah. Plus C2 e to the 2x plus c3 e to the 3x plus, that's your complementary solution. Your particular solution was this one up here, not a plus but a minus. Oh man! Okay. Your solution up here, minus 11/12 minus 1/2 x. There is your general solution for this. We knew this already from the example 9. This we got from here, and the combination of these three linearly independent, arbitrarily constanted, equations. This forms your complementary solution. That was your particular solution, because that did solve that. We just showed it did. So the combination of those gives you your general solution. Okay. Now, that leads, and I've been saying that already existed, to another superposition principle, and that is this one. It seems very similar to the previous one. It just has the y sub p's in it. And not just one y sub p, but a bunch of y sub p's. Let's let y sub p sub 1, y sub p sub 2, y sub p sub 3, I got subs on subs on subs, comma, dot, 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 comma, y sub p sub, now what do I use as this one? K. Be particular, so be K, particular solutions to the non-homogeneous linear nth order differential equation. Now this is referring back to number 7, the part that had all those n derivatives, blah, 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 equal to some g of x. If that g of x has k different particular solutions that are all solutions for that, as well as the n solutions, linearly independent solutions we're going to get from the homogeneous part, that would be your complementary solution, okay, the combination of all those, on an interval I, corresponding in term and this will be to k distinct functions supposed to be a CT. It went really bizarre. G sub 1 of x, G sub 2 of x, G sub 3 of x, dot, 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 up to G sub k of x. So you see each of these particular solutions are to some g of x, okay? But these are all added together to make your right-hand side the overall g of x. But if you can split that into composite or component functions of that, and each one of them has one of these particular solutions. Now, they do that is. Now, almost seems like to me they start going and just drop a thought mid-stride and then throw something else in. That is, suppose that y sub p of x, y sub p, now is it k this time? No, it's I. Y sub p sub I denotes a particular solution to the corresponding differential equation. They really know how to make this so bizarre. Here's that one, will be your a sub n of x, y to the nth derivative of y with respect to x, they don't put the y of x, so I'll start leaving them off too, plus a sub n minus 1 of x, they do put it there, y to n minus first of x, they're not putting the of x, I keep forgetting that, plus dot 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 plus y or a sub, I'm going to start with 3 of x, y, the third derivative of y with respect to x, plus a sub 2 of x times y double prime of x plus a sub 1 of x y prime plus a sub 0 as a function of x times y equal to, goodness gracious, this, yuck, equal g1 of x. Okay. Now, in other words, all this is your homogeneous part when that is equal to 0. You're going to come up with a linear combination of C solutions, what is it? Yeah, N solutions, and that's going to be your complementary part. Those N solutions with the arbitrary coefficients, C sub n, C sub 1 to C sub n, with each of those. But then you got a G1 of x, and this y sub p of 1 will be the one that makes denotes the particular solution for this G1 of x. And then you may have more G1, G's of x, and then you have a different y sub p2, y sub p3, and so forth. Each one of them corresponding to a different component of your solution. Okay? Now, with that in place, then your y sub p of x, which will be it's not a linear combination, it's just a combination of y sub p sub 1 of x plus y sub p of sub 2 of x plus y sub p sub 3, that's supposed to be a p, of x plus dot 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 all the way up to and including y sub p, now what is that counter here, k? Yeah, sub k of x. For every g of x you have out there, it could have its own particular solution, and these correspond to this. So your overall particular solution will be not a linear combination, but just a combination, a superposition of those. No arbitrary coefficients in it, just the sum of those other particular solutions. Another superposition, but with no arbitrary coefficients. Now that is a particular solution of this thing here, but now the right-hand side would be your g1 of x plus g2 of x plus g3 of x plus dot 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 plus g, what was that? K, I believe it, g sub k of x. Okay. All this stuff, that same homogeneous part, you know, this part on the left-hand side, and then to some sum of all these g's, each one of these corresponding to a different particular solution, then that superposition of all those particular solutions, not a linear combination of them, just the superposition of them, will be the right-hand side. They will be the particular solution that you'll add to the complementary solution you got from the homogeneous part. Yeah? Okay. Let's see if we can do an example that'll help it make maybe a little more sense. Well, leave that up a bit. Okay. I've left off a lot of verbiage. I tried to say it, but writing all that stuff just takes forever. And I get tired of writing it, and it gets sloppier and sloppier, and then I think, well, what's the point? No one can read this anyway. So, but that's your theorem 4.1.7 that's listed on page, bottom of page 128. Okay. And they love to prove it then with those linear operators, which just thrills me no end. Okay. All right, to erase? Okay. Example 11. It said you should verify, oh, isn't this fun, that y sub p sub 1 is equal to minus 4x squared is a particular solution of y double prime minus 3y prime plus 4y is equal to negative 16 x squared plus 24x minus 8. Okay? Okay? Okay, let's first verify that one. Of course, what you'd have to do first is y sub p1 prime is equal to negative 8x. Y sub p sub 1 double prime would be negative 8. And that's as far as we need to go because we only have up to 2. Okay? So with that in mind, let's plug in what y sub p sub 1 double prime is. Negative 8 minus 3 times your y sub prime, which is a negative 8x, plus 4 times your y, which is negative 4x squared. The question is that equal to minus 16x squared plus, I think that's a 24x, minus 8. I hope I copied it right. Yeah, I think so. Well, let's see what we got. I can tell the minus 8 is equal to minus 8, so I'll get rid of those. This gives me a 24x minus 16x squared, and there's a minus 16x squared plus 24x. Yes, those are equal. Okay? All right, we verified the first one. We need to verify that y sub p sub 2 equal e to the 2x is a particular solution. This is copying from above. Is a particular solution of that same thing, except now we're going to say it's equal to 2e to the 2x. Okay? Well, what are we going to have to do here? Say again? You know, I didn't even bother to look and see what time we started, so I don't know what time we're supposed to end. Do you have a general idea? Okay, I don't either. Let's see, we were supposed to have started at, what was it, 3:30? Was that right? No. Yeah, and go to 4:45. We started before then. You want to say 3:15? Okay. So we'll stop at 4:30. Is that all right?
3:30.
Huh?
3:30.
Yeah, I'm sorry. Okay. Yeah, okay. Because we're supposed to go till 3:45. Yeah, I'm sorry. I said the time's wrong. 3:45, and because I normally on Wednesdays have to leave by, get over there by 4:30. So yeah, that makes sense. Yeah. So we'll stop today at 3:30. Yeah. Okay. All right. So y prime of sub p2, so y sub p sub 2 prime is equal to what? Okay, you're doing the double prime, aren't you? Yeah, y prime. Yeah. 2e to the 2x, and y sub p sub 2 double prime is equal to 4e to the 2x. Oh, excuse me. Okay, let's plug that in here. Y double prime is 4e to the 2x minus 3 times y prime, which is 2e to the 2x, plus 4 y, which is e to the 2x. That's supposedly equal to 2e to the 2x. That was the right-hand side here. So let's see what we've got. 4e to the 2x minus 6e to the 2x plus 4e to the 2x. Well, 4 and 4 is 8, minus 6 is 2e to the 2x. Got it? But we have another one, that y sub p sub 3 equal to xe to the x. Ooh, this one doesn't look as much fun, does it? Is supposed to be a particular solution of this thing here, that whole first part, y double prime, all this, everything identical, equal to two x e to the x minus e to the x. 2x e to the x minus e to the x. All right. Whew. All right. What's your y sub p sub 3 prime? Product rule. X times e to the x, that's the first part, plus e to the x is the second part. All right, that one wasn't too bad. Let's now do your y sub p sub 3 double prime, and that's as far as we have to go. But what's it? Huh?
Okay.
Yeah. and y sub p sub 3 double prime. Well, the first part is going to be just like that, so that's going to be x e to the x plus e to the x. That's the first part. And then the next is another plus e to the x. So this would be x e to the x plus 2 e to the x. Right? Okay. Now let's take that and plug in to our original, which is y double prime. So that would be x e to the x plus 2 e to the x minus 3 times this. So I'm just going to write it down with the minus 3 in front of it. That's minus 3x e to the x minus 3e to the x. Okay? Plus 4 times x e to the x. And supposedly that's equal to, it drives me nuts, 2x e to the x minus e to the x. So let's see what these do. Well, here's a e to the x e to the x, minus 3 plus 4, so that's going to be a 2x e to the x, because these two add to 5 minus 3 gives us 2x e to the x. Those check off, okay? And here we have a minus 3e to the x plus 2e to the x will be a minus e to the x, which is exact, I said e to the x for x to the x, minus e to the x, and that's equal to, yes, those check too. So all of those work for the various pieces. Now that was just the given, okay? Now, I've got to erase some stuff, okay? And I'm going to erase as much as I can get away with. So this is a particular solution to that. There's a particular solution to the same thing, only it's equal to, uh-oh, I erased too much. Yuck! Okay. Let me go on and erase some more while I've got the eraser up. I'll try to leave that, but I need to leave. These were just all verifying what they were telling us was true. I'm going to have to come back and fill in a lot of blanks because I erased too much before. Okay. So this is a particular solution to this thing equal 2e to the 2x, 2e to the 2x. And this thing is a particular solution to this thing equal that. Okay? Now, since you know those are true, I think they left off, if you're looking on page...
right here at the bottom.
Yeah. This is a particular solution.
Is that x to the, just x to the ex?
x to the e, x e to the x.
Okay.
I think. Yeah, x e to the x, yeah. This one is e to the 2x, and that was minus 4x squared. Okay? Now, all those had the same left-hand side with just different right-hand sides. And these are the solutions that make the right-hand sides true, the particular solutions. Now, one thing I think they left off here, on page 129, just below where all that's written, they say y is equal to y sub p1 plus y sub p2 and y sub p3. I think that should be y sub p is equal to y sub p1 plus y sub p2 plus y sub p3. Because later they're going to be y being the general solution, and I don't think you should mess it up like that. So, what if now we have, this is our differential equation. Linear, higher order, second order, y double prime minus 3y prime plus 4y equal, and you just add all these together, minus 16x squared plus 24x minus 8 plus 2e to the 2x plus 2x e to the x minus e to the x. What if that is your right-hand side, your g of x? But the g of x is broken into a polynomial equation, an exponential equation in 2x, and another exponential equation in x. Okay? If that's the case, now, they don't tell you what the and here's where things get a little, I think very squirrely. Okay? They start putting C's in here, but in order for the C's to be there, they must be in the G's as well. Okay? And before they said, do not put arbitrary coefficients in there. Okay? Now these C's are constants, not necessarily arbitrary coefficients. So what if we had, now this is all they're going to do with that one, that your particular solution would be the combination of the superposition of those three. That's all they're doing there. That's where the little brown box comes into play. That ends example 11. They move on as if it's part of it, but it's not. So I'm going to erase this part and go back and show you what they're doing here. And this sort of gripes me sometimes. Sometimes they give the solution, then give the where it came from. Other times they give where it came from, then give the solution. They're now giving the solution y sub p. This has nothing to do with the ones we were just talking about. Is equal to C1 y sub p1 of x plus C2 y sub p2 plus C3 y sub p sub 3 plus dot 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 all the way up to plus C sub, now which one do they use here? K y sub p sub k of x. Now they didn't put the of x there. All right, now that looks like they're doing arbitrary coefficients. These are not. These are just constants, okay? Where these are constants is also a particular solution of 14, trying to find 14. That was the very last thing that we did in the theorem 4.1.7, where the right-hand member of the equation is now just not g1 of x, but g2 of x, but gk of x, but now that is c1 g1 of x plus c2 g2 of x plus c3 g3 of x plus dot 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 plus c sub k g sub k of x. Okay. All right. Now, I wish they just named the constant different or something like that. This is not saying you make an arbitrary combination, linear combination of things. That's not what it's saying at all. It's saying if your right-hand side of the equation, the non-homogeneous part, was some g that you did know the particular solution to, another g you knew this particular, and this one, but these have constants in front of them. You put the same constants in front of those particular solutions. This isn't saying that you make these are not arbitrary constants. These are the same constants that were in front of the g's here. And these are the particular solutions for those particular g's. Yeah, this is the right-hand side, and this would be your particular solution that would fit this if that was the right-hand side. But that's the particular solution for this one, that's the particular solution for that one, that's the particular solution for that one, that's the particular solution for that one, this one. And if you have a c's in front of these, you put the same c's in front of those. It's just that the constant carries up there. It's not arbitrary, that's the same constant as you would have there. Now that's assuming you knew this was the particular solution of that without the c in front. You put the c in front, you have to put the c in front of that. It looks a lot like arbitrary. They're not. They're just constants. Okay. Now, they have some remarks at the bottom of that page. And there's really, say again? I can't hear you.
I said good grief. I got to go all the way back to 1.3.
Oh, okay. And I probably didn't do very much on the 1.3 one either. But what they're saying here, a dynamical system whose rule or mathematical model is a linear nth-order differential equation, just like we've been doing. But now, for some reason, they have a sub n as a function of t, not of x. So this doesn't really matter much, except they're implying, when they say dynamical model, that these are functions of time rather than position, okay? I don't think it really matters, but for some reason they put in the t's. And I'm assuming there is a reason for that. And the everything's a function of t now, not of x. Even the right-hand side, g of t. But what they did say is whether the y's are also functions of t. I think they have to be, because that what you're taking the derivative in respect to has to be your independent variable. They don't say it, but it is. Okay. This is said to be an nth-order linear system. Nothing new there. The n time dependence, now they are calling them time-dependent functions, y of t. Now, here they're saying they're time-dependent. The y of t, y prime of t, y, the n minus first derivative of y with respect to t are what they call the state variables of the system. Okay? Recall that their values at some time t give the state of the system at that time. The function g is called the input function or the forcing function, which gives the state of the system, but it tells you either where to begin or where to go from there, okay? The forcing function, okay? Input function. The solution, y of t, that's going to make those true is going to be your output or response of the system, okay? And under the conditions stated, blah, 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 I don't think I'll go into it anymore. Anyway, we finally finished 4.1. Now, I've given most of these before, but just, okay. Any of the odds are in the back of the book, 1 or 3, 5 or 7 if they're in the back of the book, 9 if it's in the back of the book, 11 if it's in the back of the book, 13 if it's in the back of the book. That was 4.1.1. 4.1.2 for the homogeneous portion. That would be any of the odds 15 to 21 if they're in the back. Do them. Any that you want to do of them. Any of the odds 23 to 29, excuse me, if they're in the back. And then 4.1.3, the stuff we started today, will be any of the, either 31 or 33 if that's in the back. Do those, whichever one you want to. 35 if it's in the back, and that's all, folks. Now, if any of the discussion problems are in the back, you can do those as well. Most of the time, they are not. But then what they were talking about right at the end of 4.1.3 said before we actually start solving homogeneous and non-homogeneous linear differential equations, we need one additional bit of theory, which is presented in 4.2. And this is called reduction of order, as if there was any order to begin with. Now it's being reduced. No, I'm just kidding. Okay. In the preceding section, we saw that the general solution of a homogeneous linear second-order differential equation, a sub 2 of x, y double prime, plus a sub 1 of x, y prime, plus a sub 0 of x, y equals 0, is a linear combination of a two-parameter system. Y is equal to C1, Y1 plus C2, Y2. Y1 and C1s are solutions that constitute a linearly independent set on some interval I, and then beginning in the next section, we examine a method for determining those solutions when the coefficients are constants. Can't wait to get there, okay? That method, which is a straightforward exercise in algebra, breaks down in a few cases and yields only a single solution, y1, of the differential equation. It turns out we can construct a second solution, y2, of a homogeneous equation, y1, even when the coefficients of y1 are variable. Okay? We're not doing those yet, but we will later. Provided that we know a non-trivial solution, y1, of the differential equation. So the basic idea in this section is that equation 1 can be reduced to a linear first-order differential equation by means of the substitution of the known solution y1. Second solution y2 of 1 is apparent after this first-order differential equation is solved. Now, they can mix this up with so many words that makes it almost difficult to follow. But this is what they call reduction of order. Suppose that y1 denotes a non-trivial solution of your equation that's at the top there. A sub 2 of x, y double prime, plus a sub 1 of x, y prime, plus a sub 0 of x, y equals 0. Homogeneous, okay? Now, notice a lot of what they've been saying, if these constant coefficients, these coefficient functions, are actually constants. That's what we're going to deal with in the next section. We're not going to deal with functions of x. If they're variable, that's what we do in the next, either the next chapter or the one after that, somewhere up there, we'll deal with variable coefficients. Now we're going to deal with constant coefficients, so that's what we're going to start off with. But they still write it this way, okay? Now the basic idea is that this equation can be reduced to a linear first-order differential equation by means of a substitution of the known solution y1. Second solution y2 of the same equation is apparent after the first-order differential equation is solved. Goodness gracious. Got about 5 minutes, so let's see. Okay. Okay. We seek a second solution so that the set consisting of y1 and y2 is linearly independent on I. But recall from section 4.1 that if they are linearly independent, their quotient y2 divided by y1 is non-constant on I, on the interval. That is, y2 divided by y1 is some new function u of x, not a constant, but u of x, and y2 is equal to u of x times u of y1 of x. Looks a lot like what we did before with our integrating factors type thing. The function u of x can be found by substituting y2 is equal to u times y1 into the given differential equation. This is called reduction of order because we must solve a linear first order differential equation to find u. Okay. Let's see what we can do with this. Here's example 1. That's a lot of blah, 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 and it sure seems like there ought to be a simpler way of stating it. So here is a solution. y1 is equal to e to the x. That is a solution to y double prime minus y equals 0 on the interval minus infinity to infinity. All real numbers. All real numbers. Okay? It says find use reduction of order to find a second solution, y2. All right, now first let's just do a quick check. All right. If y1 is e to the x, y prime of that is e to the x, right? Y double prime of that is e to the x, and y double prime minus y is equal to 0. So e to the x minus e to the x is 0. So yeah, we verified that. That's everywhere on all real numbers. That will work. Okay. Now, if you tried to come up with a different solution, well, sort of giving it away now. You probably come up with that same one again. You know, there's got to be another because it's a second order differential equation. You need two linearly independent solutions. So we need to come up with another one, but just looking at it, it's not completely obvious what that would be. So here's what they say: use y is equal to, and that's y of x, but they don't do that, u of x times y1 of x, okay? Which is, in this case, u of x e to the x, okay? Now, what we want to do is do y prime. And what would that be? Let's use this formula here. The second one, y prime. U of x be e to the x plus u prime of x e to the x. which is u of x plus u prime of x times e to the x, right? You can factor out e to the x, okay? Okay. I don't know if that was a smart move to make, but it's true, okay? All right. Okay, let's do y double prime of x. Let's use the one that you did rather than the one I did. That may make it more complicated. What would this be? Take the derivative of this derivative. U to the x, u of x, I mean, e to the x, right? E to the x, u prime of x. Okay, that's the first one. Let's do the second one. Okay, you just took the derivative of this one here, so now take the derivative of that. U prime of x, e to the x, plus e to the x, u double prime of x. All right. Now, we can simplify that as u of x, e to, we can, see if they do it. Yes, they do. Well, I'll do it in two steps. Plus, let's combine these two, because these are identical, to e to the x, u prime of x, plus e to the x, u double prime of x, which would be e to the x times u of x plus 2u prime of x plus u double prime of x. Okay. All right. Now let's subtract them. Okay. I didn't have to pull out the e to the x. So let's go back to our original. Y double prime minus y. Y double prime, let's go back to this one, is u of x, e to the x, plus 2e to the x, u prime of x, plus e to the x, u double prime of x, minus u of x, e to the x. Yeah, that's what this was, y. Okay? And this is supposed to equal 0. Okay? Now, here's a u to the x, e to the x, minus u to the x, e to the x. So what do we have now? 2, I keep wanting to pull that out. Let's do it. E to the x times 2u prime of x plus u double prime of x is equal to 0. Well, e to the x is never equal to 0, so you can divide that out. And now we have this thing, okay? E double prime plus 2e prime is equal to 0. Now we're going to do this thing that we've done a few times before. Let's take our prime here and make that w. Let u prime of x equal w of x. Okay? And what we've just done is reduce the order. Okay? So what we have now, u double prime would be w prime plus 2w is equal to 0. So now we've made a second order differential equation into a first order. Here was the second order. Now we've made it into a first order. Okay? Now, which is a linear first order equation in W. And then, yuck, I'm going to erase a bunch of this because we don't need it anymore. And I think we've gone way over, haven't we? Let's finish it. Okay, I'm all in favor. Okay. I don't think we need this anymore, because this is all getting to the point of where we were. Or that, or that, or any of this. I sure hope I don't need it anymore, because so I've just erased it. Okay. Scratching up my screen like crazy, all this erasing it. Hopefully it won't destroy it before I'm retired. Okay. All right. So we have a linear equation in W and X. Okay. How do we solve this? Yeah. Let 2 be the p of x, and we're just going to integrate 2 dx, and that gives us 2x, and then raise that to the e, you e it, okay? That's our integrating factor, and we have e to the 2x w prime plus 2e to the 2xw is equal to 0. Okay? Now, hopefully, we've made this a perfect derivative. D of e to the 2x times w. Let's see if we did. First times root of the second, yes, plus second, which is w, times root of the first, which is 2, e to the 2x. Yes, it is. Okay? And that's equal to 0. Okay? So that means that if you integrate both sides of this, you'll get e to the 2xw is equal to some constant. Right? So w is equal to c e to the minus 2x. Okay, we'll call that C1 is what the book calls it. W is equal to C1 e to the minus 2x, or what was W? U prime. So this is equal to U prime of x, which means then that we can do a du by du dx. Make sure I'm going to do this right. Yeah. So du dx is equal to c1 e to the minus 2x. So let's put that in differential form and then integrate both sides of this, and you get u is equal to c1 you get from this. Antiderivative of that. E to the minus 2x. Yeah, it's going to have a minus in front and a 1/2 in front. Say again? And I think plus the C2, isn't it? Yeah. Minus C1 over 2, which is basically what I said, e to, whoa! Yeah. Yeah. Now, if we go back to our y here, y is equal to u, which is negative 1/2 C1 e to the minus 2x plus C2 times y1 of x, which was e to the x. Okay, remember that was way back at the beginning. So this now would be y is equal to minus 1/2 C1 e to the minus x plus C2 e to the x. Is that right? Yeah. Okay. Now, here's the part that kind of drives me nuts. They say, by using C2 is equal to 0 and C1 is equal to 2, we get the desired solution of y2 is equal to e to the minus x. Okay? Now, in my mind, just say this is a new constant. Why say it equals 0 equal 1? Because this is now your first part that you started with, and this is your new part. So let this be C1 or C3 or whatever you want it to be. But now you have two linearly independent solutions. y1 is c e to the x, y2 is c e to the minus x. Okay. Now, I know we're out of time by this thing. So let's start next time at the top of page 133. Okay. General case. Okay. Now, did we get far enough for any? It's a very short section, so I think you can probably do some of the odds 1 through 15. Okay. If they get too messy, stop, and after we do example 2, maybe we get, or general case and example 2, maybe some of the rest of them will make more sense. Okay. As soon as we can get through with this, we will then be ready to start actually solving homogeneous linear equations with constant coefficients. We go back really to the homogeneous case and work with it. Then 4.4 will be the undetermined coefficients. That'll be solving the particular, okay? And then I think we're going to skip the annihilator approach in 4.5. I think we'll be through with, okay, no. Then we'll jump to 4.6, variation of parameters. I was thinking that was a new chapter, but it's a new section. All right, any questions? Or I know this is sort of came fast and furious at the end, but we did all that, and for the life of me, I can't recall if we use that again. Okay, I think we do in one circumstance, and then once we get the general rule down, we don't ever go back and do all that over again. But we'll get the general rule. But this isn't the general rule yet, just to show we could come up with a second function given the first one. And but boy, kind of a messy way to go about doing it. All right, okay. Okay to erase?